This video is on operating with radicals. I'm going to be looking at multiplication and division. For multiplication, when we multiply radicals, we want to multiply the coefficients together and the radicands together. But we must have like indices. So we always need to have like indices. So even with addition and subtraction, we have to have like indices, but the same radicand. Multiplication, we have to have the same indices, but the radicands can be different. Then we want to simplify. There are two ways of doing this problem. We have the square root of 12 times the square root of 18. There are two ways. I'm going to show both ways. The first way is we can multiply to begin with and then simplify. The second way is we could simplify the individual radicals first and then multiply. So I'm going to show both ways. So the first thing I'm going to do is I'm going to see, do these have the same index? They are both square roots, so that means I can multiply. So just as if I were to simplify a radical, I would separate them into two radicals, one being a perfect square, one not being a perfect square. That's very similar to this. That means that I can multiply these back together. So my first way, this is my first way, I take the square root of 12 times the square root of 18, and it will equal to, since both of these are inside the radical, so these are our radicands, I will do the square root, one big square root of 12 times 18. Because they are in the same type of radical, I can put them together. Then I would have the square root of 12 times 18 is 216. Now I want to simplify the square root of 216. Now that I have it under one radical, I want to find the largest perfect square that goes into 216. This would be the same thing as the square root of 36 times the square root of 6. Well, the square root of 36 is 6, and then the square root of 6 stays as 6. So as always, we can always check our answers using our calculator. So I'm going to type in the original of square root of 12 times square root of 18. So square root of 12, I got to get out of the radical, times the square root of 18, get out of the radical. I get this decimal value. Then I want to type in my answer of 6 square root of 6. 6 square root of 6. It is the same decimal value. That means that this method works. I also want to show the other method, which could end up being a longer process, because what's going to happen is I'm going to show you that you can simplify these ahead of time, multiply the coefficients together. See, this one has a coefficient of 1, this one has a coefficient of 1, so it did not affect the problem. But if I were to simplify them, they will have coefficients, and they will still have radicands. So we would have to multiply the coefficients, then multiply the radicands, and then potentially have to simplify the radicand again. So sometimes this could be a longer process. So I want to take the square root of 12 times the square root of 18, and I want to simplify these first. I should end up getting the same answer in the end. Again, this is just a different way of doing this problem. So the square root of 12, I want to rewrite this as the square root of 4 times the square root of 3. This is the square root of 12. Times the square root of 18 is the square root of 9 times the square root of 2. These will simplify. For the square root of 4 and the square root of 3 will simplify to 2 square root of 3 times, then the square root of 18 becomes 3 square root of 2. I did not mean to put that times right there. I'm just going to use whiteout to take that off, because it's just 3 square root of 2. I don't have to put times square root of 2 because I know this is just 3 square root of 2. Now, this is not my final answer because I know that I want to try and get it all together. Now we can go to the part up here that says multiply the coefficients together and then multiply the radicands together. because these are still square roots, I want to multiply my coefficients. My coefficients here are 2, my 2, and my 3 as my coefficients. So this is the same thing as 2 times 3. This is my coefficients. And then I need to multiply my radicands together. Because these are both underneath the same type of radical, I can multiply my radicands together. And I know I will still have the square root symbol. Keep that in purple. This becomes, my first radicand is 3 times my second radicand is 2. This will end up being 2 times 3 is 6. We have the square root symbol. 3 times 2 is 6. And we do end up with the same answer, but this process can sometimes take much longer, but it sometimes is easier if you don't have a calculator to do larger numbers. This gave you a very large number to try and find the perfect square of. This one has much smaller numbers to try and figure out the perfect squares. So square root of 12 is easy to simplify, square root of 18 is easy to simplify. And then we could potentially simplify the square root of 6 if we had to. This method, the first method, the square root of 216, if you don't know your perfect squares automatically, then it might be a little bit harder to do. So both answers are still the same, so both methods would still work. Moving on to division, we end up having the same thing. We again must have like indices. We want to divide the coefficients if possible already, put the numbers underneath the same radicals, and then divide. So if we already have coefficients, we do want to simplify those ahead of time if we can. As long as these are the same indices, we can put these together as one fraction. Just like we can put the multiplication as one radicand, we can do the same thing with division. So in this case, the coefficients are 1, so we don't have anything to do there. We can put these radicands together because they are both underneath the square root. So I can rewrite this as the one big square root symbol of 18x to the 5th as our numerator, divided by 2x cubed as our denominator. Now the reason we do this is if we can divide these and get something without a fraction, that's the best thing we could do. However, radicals cannot be left in the denominator. So this is one of the reasons why we want to simplify if we can. This one has a radical in the denominator. I don't want to have to rationalize, which I'm going to talk about in just a second, if I don't have to. If I can simplify this, I want to. So we look to see 18 divided by 2 is simplifiable. So I have the square root of, I know 18 divided by 2 is just 9. And then x to the 5th divided by x cubed is also able to be simplified. That becomes x to the 2nd power, because 5 minus 3 is 2, so x to the 2nd power. I no longer have a fraction, so there's no way I can have a radical left in my denominator. So this makes more sense than trying to rationalize ahead of time. So now we can just simplify the square root of 9x squared. The square root of 9 is 3, and the square root of x squared is x. So our answer is just 3x. So going on to radicals cannot be left in the denominator, this is when we would have to do what's called rationalizing the denominator. I'm going to write that out. Rationalizing the denominator. Rationalizing the denominator. Because we want a rational number in the denominator. Right now, the square root of 15 is an irrational number. So I don't want to have the square root of 15 in the denominator. However, I do not want to go straight into rationalizing if I don't have to. I want to try and simplify everything as much as possible before I have to do anything that could potentially make this process even longer. So for dividing, these do have the same index. These are both square roots. I want to see if I can divide the coefficients. 2 divided by 1 will not simplify. But then I want to know if I can simplify the radicands. 5 over 15 is possible. So just like I can put my 18 and 2 into one fraction, I can do that without having to rewrite it as one fraction. I could simplify 18 over 2 as they were, and I still have 9. I could simplify x to the 5th over x cubed as they were, and still have x squared in the numerator. That's the whole point of understanding numerators and denominators and how to simplify fractions. So in this case, I do want to simplify this as much as possible now. So if I were to rewrite this, my 2 as a coefficient has to stay as 2, and it is in the numerator. So I might have a denominator depending on how my radicands will simplify. I have the square root of 5 over the square root of 15. So I want to talk about 5 divided by 15. 5 over 15 is 1 over 3. So I will have 1 over 3 left over inside the radical. So I have the square root of 1 over the square root of 3. This square root of 1 over the square root of 3 is the same thing as the square root of 5 over the square root of 15, because I still have the square root symbol. Now, the square root of 1 is just 1, so I could actually still rewrite this even further as just 2 times 1 is 2 divided by the square root of 3. This is simplified, but it is not it's not simplified completely. We do not want to have a radical in the denominator of our problem. This is when we come to rationalizing the denominator. Rationalizing the denominator, I'm just going to rewrite this part right here, 2 divided by the square root of 3. Rationalizing the denominator is when we take the denominator and we want to get a rational value. We want to get rid of the square root of 3. So how do we get rid of a square root? Anytime you square a square root, it gets rid of the radical because they are inverses of each other. I cannot just square the square root of 3 because then that will change the value and it will undo everything that we've done. We can't just square it, but we can multiply it by something. As long as we do not change the value of anything, we can manipulate it to look like something different. Squaring something is basically saying that value times that value. So if I want to square this part right here to get rid of the square root, but without actually just squaring it, I would multiply the denominator by the square root of 3. But because I am doing something to the denominator, I also have to do something to the numerator to keep it the same value. So I would have to multiply the numerator by something. If we understand to keep the values the same, I want to keep the value the same. When I multiply, the value you can multiply by no matter what to keep it the same is 1. You can multiply anything by 1 and it stays the same. However, you do not just have to write 1 like a 1. 1 can be written in different representations. So if I have the square root of 3 in the denominator, what divided by the square root of 3 will give me 1? Anything divided by itself will give you a 1. So that means if I multiply by the square root of 3 on the bottom, I also have to multiply by the square root of 3 on the numerator. Because this is equal right here, this is equal to 1. This is why we are allowed to do this. We want to because the square root of 3 squared will get rid of the radical in the denominator. Radicals in the numerator is fine. But the reason we're allowed to do this is because this value is 1. So now we just actually multiply these. 2 times, so numerator to numerator, 2 times the square root of 3 is 2 square root of 3 because coefficient, radicand, over. The square root of 3 times the square root of 3 will become the square root of 9. This does happen, but the reason we see this, do not try and simplify this now. The reason we see this is because the square root of 9 is just 3. So this will become 2 square root of 3 on the numerator divided by the square root of 9 is 3. Because square root of 3 times square root of 3, square root of 3 squared just becomes 3. Now, we no longer have a radical in the denominator. A radical in the numerator is perfectly fine. Coefficients could potentially still simplify. So 2 divided by 3, we would want to see if that could still simplify. 2 over 3 cannot be simplified further, so we know that this has to stay. Square root of 3, 3 is prime, so I know that this cannot simplify further. And there's no other radicand anywhere in the problem, so I know I cannot simplify the square root of 3 anywhere. This is a radicand. This 3 is a coefficient. These cannot go together. That means that this will be our final answer. And again, as always, you can check using your calculator if you get the same decimal value. So using my calculator, I'm going to type in the original problem. This one's going to be a little tricky. I want to type in my numerator. I'm going to put parentheses around my numerator so I can keep it all together. I have 2 square root of 5. I have to get out of my radical, then close my parentheses, that's my numerator, divided by, I want my denominator to all be together, the square root of 15, get out of my radical, and then close my denominator. I get a decimal value of 1 1500ths. Now I want to check my answer. So again, I'm not going to clear this. I want my numerator together, which is 2 square root of 3. I have to get out of my radical and then close my numerator, divided by my denominator is just 3, only 3, so I can just put 3 there without a parentheses. Press enter. I get the same decimal value. That means that these are correct and it has been simplified. And because my radicand is 3, it's prime, I cannot simplify that further. I have no radical in the denominator, and 2 over 3 cannot be simplified further. That tells us that this one is simplified completely. So this is rationalizing the denominator. If we have a square root of 3, we wanted to end up squaring it, so we just had to multiply it one other time to become a squared. Rationalizing the denominator can get more complicated if you have different types of roots. So we will see that in a separate video.